Okay, guys, welcome back. In a long week. Couple of things. Just a reminder: the exam is open now. It'll be closed tomorrow at 10 p.m. So, chapter 7 through 9. Gotta make sure not to forget that. Okay. A couple other things too. And I'll make an email and send it out to you. The final exam, it basically is a set date. With exams, I know work schedules and so forth. I have a little bit of leeway to assist you, but I don't have any leeway at all with the final. Okay, so think ahead about your schedule for the final because once the final's done, I got the grades all set up. I get a post them right away. So look at the schedule. All right. Any questions? Anything you need to discuss? No. All right. Well, we were on chapter 10, specifically slide 8. And let me just back it up because, being a week, we were writing. This chapter deals with reactions, and there's 6 types of reactions that we're going to be working with. And we're going through some examples. We've talked about balancing the equations. The balancing the equation is very, very important. It'll be much more important down the road as we get into calculations and so forth. Okay. Some of these equations you can only balance really by kind of trial and error, so to speak. Put a number here, go back and forth until the number hits. Some of these reactions will have a very specific method by which it would aid you into balancing that chemical reaction. Okay, so we talked about these reactions and balancing them out. Then we started getting into writing reactions from words, and this is where what comes into play is we were learning how to put formulas together, how to put ions together, make compounds, both ionic compounds and covalent compounds. Okay, so we start learning the names of them so you can put them together properly, so you can write a formula. Now we're taking these compounds and we're going to react them with each other so they can give us a product, and then we write it out, we balance it, we write the physical state, and the physical state is going to be dependent on if it's an element. Its physical state would be either solid, liquid, or gas, obviously, right? And there's only, of the elements themselves, there's only 2 liquids, about a dozen or so gases, and then the rest solids. So you got to remember that. Now, the other ones, whether they're solids or aqueous systems, the system would tell you it's aqueous, but we would depend on the solubility rules to determine whether something is a solid. And these really are based on the ionic compounds. When we deal with solubility, majority of the time we're dealing with ionic compounds in aqueous systems. Okay, and so those are the letters we use, as we know by now, hopefully: solid, liquid, gas, and then AQ, meaning it's an aqueous solution. It's a water solution. Okay. Remember the elements that are solid, liquid, and gas, and then especially remember the ones that are diatomic, and there's only 7 of them. Have no fear of ice cold beverage. Okay, remember those. And so when they talk about, say, chlorine, there's a difference when you write the reaction of chlorine versus the reaction of chlorine gas. Normally, when gas is used in the sentence, they are talking about the diatomic, okay, chlorine. Recall that our subscript tells us the ratio of each atom with respect to the compound. Those are whole numbers, and there's a specific ratio. Okay. Now, the coefficient is that number in front of the formula. Now, once we set the coefficient in its proper number, we leave it alone. We don't change it. That's it. That's the coefficient for that particular compound. Excuse me, that is a subscript for that particular compound. The ratio between the atoms for that compound. The coefficient, the big number in front of it, we can change all day long. We can put any number we want up there, because that is telling us how many of those molecules we need. In this example here, we're saying that there are 3 molecules of H2O or water. The one on top with no number, it's understood to be 1, just like mathematics. No number in the letter in algebra, it's understood to be a 1 value. So the top example is a 1 molecule of H2O. Okay, so that being the case, we got into, okay, here's a sentence. We need to convert the sentence into a chemical reaction, okay? And here it reads, sodium reacts with chlorine to produce solid sodium chloride. All right, so sodium, we know, and they're not talking about sodium chloride or sodium anything else. They just said sodium. That means that we are talking about the elemental sodium, okay? The metal sodium. And we know that, hopefully, that I had presented to you a periodic table that listed the solid, liquid, and gas elements. Sodium is a metal, and there's only one metal that's a liquid. So all the other metals are solid. And that's why I know that sodium is solid, because it's not the other liquid metal. If you might want to go back and refresh your memory which metal that is liquid at room temperature. All right, so we got sodium right here, and then the keyword reacts. So that tells me that's my plus sign, okay? Because sodium is reacting with something else following the react word. And here we have chlorine. Note they're talking about chlorine. They're not talking about chloride. Chloride is the ion. Chlorine is the element. We also know that chlorine is diatomic. Okay. Now, can anybody know what chlorine its state is? Is it solid, liquid, or gas? Okay. Give us some thought. Come back to you. The keyword produced is the arrow. Okay. Produced tells me that that is reactive. We got an answer on that. And chlorine is a solid. Not quite. Okay, not a solid. I'm going to leave this blank. Okay. So produce is the key word for the arrow. Okay, you might see to produce or gives or anything that says, okay, here's my reactants now, here are my products. Now, the products that are following that produce are here, sodium chloride. Now, you can see 2 things. They're talking about chloride, like earlier it said chlorine. But chloride should indicate to you that we have let's see what the answer is, and it's a gas. That's correct, Christina. It's a gas. Okay. And so chloride tells us that we have an ion. Okay. So we go back to the periodic table because I don't remember what the charge is, but I know where it's at on the periodic table. And on the periodic table, I find chlorine to be in part of group 7. That tells me that, okay, chlorine is in group 7 as an element. When it becomes an ion, it's a nonmetal. It's going to gain an electron. And because it's in group 7, it's only going to gain 1 because it's looking for that happy 8, that octet rule. And so chloride will be a Cl negative charge, okay? Sodium. Well, we know the symbol. I just wrote that down, but we're talking about an ion here because it's combined with sodium chloride. Excuse me. Question is what charge? Well, since we figured that chloride is a -1, it just tells us automatically that sodium has to be a +1, right? Because when they come together, or is that right? No. Well, maybe that's incorrect because how do I know that sodium has to be a +1? Well, I don't. Just what I just said. I assume that it's going to come together. Point being is, don't make that assumption. Okay. So let's take this off and refresh your memory and remember that sodium is a metal. And obviously, being a metal, it's going to lose electrons, so therefore it's going to have a +1 charge as an ion. Question is, well, how much of a plus charge? We find it on group 1. It's telling us we got 1 valence electron. It's going to lose 1 valence electron, so it becomes isoelectronic with neon. Okay, losing 1 electron now, we can say unequivocally that it's got a +1. Okay, so those are the ions. So now we can put the formula together. It's a 1-to-1 scenario, so I can write down sodium chloride solid. Now, how do I know solid? Because they told us it's a solid. Okay, no aqueous system occurring here. So we got sodium chloride. Now we got the key components, the formulas written. Now we got to balance it. Okay, and so you can see sodium is balanced here. We're 1 sodium, 1 sodium. We're good to go with sodium. But we got 2 Cls as a reactant, but only 1 as a product. Well, what if I put a 2 in front of sodium chloride? Okay, well, that balances my chloride, my Cls, but it kicked up my quantity for the sodium. Okay, no problem. I go back to the reactant site and simply put a 2 right there. Now I go back and check. Okay, is everybody happy here? I got 2 sodiums, 2 sodiums, 2 Cls, 2 Cls. Okay, we're balanced. So remember, it's understood that there's a 1 here. Normally it's not written. So we got a ratio here that requires 2 sodium for 1 chlorine to give us 2 sodium chlorides. And the fascinating thing about this reaction is this. This sodium metal is very reactive, extremely reactive. Okay, put it in water, it reacts like crazy. It gives off a lot of heat, gives off hydrogen gas, enough heat to explode. Okay, then we got chlorine, which is a poisonous gas. Okay, used a lot in water treatment plants to clean up the water. So be careful if you ever see a cloud of yellowish green tinge color coming at you. That's fluorine gas. Get out of the way. Poison gas, reactive metal. We can put this stuff on your French fries, sodium chloride. And the only thing that happened was there was a transfer of an electron from the sodiums to the chlorine, give us the chloride, 2 chlorides. Simple thing, 2 electrons, which are, you recall, with respect to mass compared to the proton and the neutron, is essentially 0, you know, and giving us that change of electron gives us products that are totally different properties of what the reactant started off with. The power of the electron. So we write down the equation like we just did. Okay, we added the states here. Okay, and then of course, you know, they're asking you here, why isn't it 2 chlorides? Okay, for the sodium, because again, we know that sodium ion is a +1. And if it was written as NaCl2, that would infer that sodium is +2. But that can't be the case because sodium is in group 1. It only has 1 valence electron. If sodium was a group 2 element, yeah, that could be correct, like barium and magnesium. That would be correct for having 2 chlorides. All right. And then, of course, we balance it like we just did. All right, so here I think this is the one where we ended up. Here's another example. Is in this case, we're taking aluminum, okay, reacts with bromine to produce solid aluminum bromide. Okay, well, let's first write down what we got. We got aluminum, Al, right here, reacts. Okay, that's my plus sign. I know that aluminum is a metal, and all metals are solid except one. This one is not a liquid; it is a solid. Okay, reacts as my plus, and then I get the similar scenario as we did with chlorine. We're talking about bromine, and so we're talking about the element which is diatomic. Anybody know the physical state of bromine? solid, liquid, or gas. Okay. What do we got here? All right. Yes, both of you are correct. It is a liquid. Only one of two liquids in the elements. The other one is the metal. Okay. All right. Then it produces is our arrow, telling us that's what we're going to make now. It's our arrow for the reaction. And then we have solid. Here's our physical state. Aluminum bromide. As we had the one example earlier, we are dealing with the ionic or the ion bromine of the ion of bromine, which is bromide. Again, like chlorine, it's in group 7, so bromide will be a -1 charge. Write the products in element in ionic form first, so you can put them down properly with the right ratio. So we got aluminum. We know it's in group 3. Okay, as it's a metal, it's going to lose those 3 electrons and give us a +3 charge. All right. That being the case, we see here that we need 3 bromides to balance out the +3 of the aluminum. Therefore, our formula would be aluminum bromide. Okay. And we know it's a solid because it's given to us. And we can write the physical state. All right. So we got the formula written down. We got the physical states written down. Everything looks okay. Now the next step is to balance it. And in this scenario, if you look at, we got 3 bromides here, two BRs over here. I got 1 aluminum, 1 aluminum, but we got a dissimilar number here. We can look for a common factor, can we not? Like we've been doing before when we came up with, remember that example that we had maybe iron 3 coming together with oxide? Remember that? Okay, we had a dissimilar charges, so we look for a common factor, which was 6. Okay, so we had 2, formula became, oh, that's an iron 2 plus oxide 3. Okay, we use common formula of common number. Well, we could similar scenario here. Okay, what if I put a 3 here and I put a 2 here? That would balance the BRs on both sides. Okay. And I call them BRs because over here on the left side is bromine, and then over here on the right side is bromide. And sometimes it's like, whoa, it gets a little confused. So BR doesn't make a difference. It's BR. It's going to be the ide or the ide or the ene. Okay. So I got 6 and 6. We're good to go. That kicked up my aluminum. No problem. We put a 2 in front of aluminum, and we are balanced. So double check. We got 2 aluminum here, 2 here. 6 BR on the reactant side, 6 on the product side. We are balanced. So this reaction is good to go. Do note the ratio between aluminum and bromide. And I say, well, why is that? Because that is a specific ratio that we can utilize in the coming chapters. Let me get rid of this real quick. You might say, well, why? Because that, ladies and gentlemen, this relationship between here and here, I can write as a conversion factor, 2 aluminum over 3 bromines. Okay, or I can write it the other way around, where I got the bromine on top and the 2 aluminums in the bottom. And these factors I can utilize when I do calculations down the road. There's also a ratio between the bromine and the aluminum bromide, okay? And there's also a ratio between the aluminum and the aluminum bromide. Okay, it's a 2-to-2 ratio here, aluminum to aluminum bromide, or a 1-to-1. With the bromine to the aluminum bromide, it's a 3-to-2. And so here I got 6 conversion factors that I can set up as needed, okay? So those coefficients are very important. We're going to use that in a chapter called stoichiometry to do calculations. For example, if I start off with 10 grams of aluminum, question may be, well, how many grams of aluminum bromide will I make? Okay. Or vice versa. if I need 100 grams of aluminum bromide, okay, how many grams of bromine would I need? And that comes into play. These ratios will come into play there. Okay. So we'll let's put down, clear my mess, and we'll bring in the reaction. So we write the proper formulas. We write in added the states as we went along, and then we balance the material. We got a 2 there, a 3 there, and then we had to balance the aluminum. And so now we have our balanced chemical reaction. So that tells me that is this. I need 2 molecules of aluminum to react with 3 molecules of bromine to give me 2 molecules of aluminum bromide. Okay, and I'm using, molecules, but I could say the same ratio applies. If I say 2 million molecules of aluminum, I need 3 million molecules of bromine, which will give me 2 million molecules of aluminum bromide. Okay. All right. So, and there's that ratio I just spoke to you about. We call these the reaction ratios. And yeah, be aware of those because we will definitely use those down the road here. Okay, one more example. They're asking you write the reaction of phosphorus reacting with oxygen to make solid diphosphorus pentoxide. Okay, oh, somebody has a question. Go back to the formula. Sure, right there. Okay. You got it, Alexandra? Okay. All right, no problem. All right, so here, let's break it down. Best way to attack any problem here is break it down through pieces. And all right, so here we ask you to write the reaction of phosphorus reacting with oxygen to make solid diphosphorus pentoxide. Okay. All right, so we got phosphorus plus oxygen. We know oxygen's diatomic. We also know it's a gas. Phosphorus, phosphorus could be a solid. Okay. Reacting tells me the plus to make. In this case, the term to make is my arrow. Now, they're asking us here, diphosphorus pentoxide. Well, my suggestion first is to write the parent formula, P and O. That's the phosphorus and the pentoxide. Then come back and check on the prefix. Di is 2, pent is 5. Okay. And so now we got 2 P2O5, and it's a solid because that's what we're given. Okay. Well, all right. Now we can balance things here. A couple of ways to do this. We got the physical states done. We can use the fact that we got a dissimilar ratio here and look for a common factor. That's one way. Or we can see we got 2 phosphorus here. We can put a 2 there to balance the phosphorus. It's like 1/2 dozen the other, whichever way you can recognize. It might be easier to use the common number here between the oxygens. The common number would be 10. Okay. 10 oxygens would balance out the oxygens. Okay. Which then kicks up our phosphorus to 4. No problem. We stick a 4 in front of phosphorus and we're good to go. And so now we see that 4 phosphorus atoms require 5 molecules of oxygen to give us 2 molecules of diphosphorus pentoxide. Okay. So it's balanced Our physical states are there. Let's see what, let me clear up my mess. Okay, we wrote down the formulas. Okay, then we gave the physical states. And then we came back and balanced it. Just like that. So looks like we're okay. All right. This one seems to be a little bit more of a problem, and we'll just do it here instead of doing it at home. But this is a typical example of what's called the double displacement reaction. Because what we do, we end up adding two reactants that are soluble in water. We mix them together, they react with each other, they exchange partners. And then if one of them is, one of the products is insoluble based on the solubility rules, then we have a positive reaction. And we do have a positive reaction because they're telling us at the end here, solid lead to sulfate. So anyway, my suggestion first before you write anything down, first write them in ions so you know how much of each you're going to put together. And so let's take the first one, okay? So the first one, nickel 3 sulfate. Well, remember that the 3, the Roman numeral 3, let me clear that mess there. The Roman numeral 3 is telling us the oxidation state of the metal. And so we're dealing with Ni plus 3, okay? Sulfate, you might not remember what that is, but hopefully you recognize the name sulfate. That would send you to the periodic table under the polyatomic ions, and you end up with SO4 negative 2, okay? Let's do the next one, lead 2, all right? So lead 2, I'll put it right here. Lead 2 is +2 oxidation state. Nitrate, again, nitrate sends you to the polyatomic ion table, and that puts us at this structure, okay? NO3 negative. And those are the reactants. So the products are produced because the keyword produces is nickel 3 nitrate. So again, let's put together the reactants first, and then we can come back and do the products. So nickel 3 and the sulfate, we got a dissimilar system here. +3 negative 2 are the charges. Find a common number again, which it would be 6, right? And so I need nickel, I need 2 nickels, and then parentheses because I need 3 sulfates, parentheses SO4 and then subscript 3. Okay. All right. Plus, lead is a +2, and nitrates are a -1. Well, we need 2 nitrates here again, so therefore I'm going to need a parenthesis. So I got lead, Pb, parentheses, NO3, subscript 2. So those are the formulas for the reactants. So produces tells us, okay, the arrow. Now, product number 1 is nickel 3 nitrate. So we still got nickel +3 and the nitrate, NO3 -1. And so you can see we need 3 nitrates. So its formula would be Ni parentheses NO3. Okay. Then the last problem says lead 2 sulfate. So we know we got lead 2, which is +2, and we know we got the sulfate, which is -2. And so it's a straightforward 1-to-1. So the formula is PbSO4 plus it's solid. So they're telling us we got a solid material. Now, all of these initially say aqueous. So this is AQ, and this is AQ. And guess what? The nitrates is HQ, nickel nitrate. In fact, if you go to the solubility table, you will find that all nitrates, regardless of what they're bonded to, are always soluble. And that's why nickel nitrate, nickel 3 nitrate is soluble, okay, and aqueous. So this, ladies and gentlemen, is a good example of a double displacement reaction. What has happened is the anions and the cations have exchanged, okay? Notice we start off with nickel here, and they exchange with the nitrate to give us nickel nitrate, okay, nickel 3 nitrate. Then the lead exchange with the sulfate to give us lead sulfate right here, okay? So the partners exchange. Now, one of these was soluble. One of the new products that was created was insoluble based on the solubility rules, and that is the lead sulfate. Therefore, you had a positive reaction, okay? So this again, oh, hold on, is an example of a double displacement, and we'll get to these here. Reaction, RXN is shorthand for reaction. Okay, so now that we have the basic formula together, now we got to balance it. Now this is the one type of reaction that we have a little bit of an A to help you to balance it. You don't have to do trial and error here. What you do is you follow the polyatomic ions, okay? Follow the polyatomic ions. For example, I have 3 sulfates on the far left side, and there's a reactant, but I only have 2 on the right side. So I could put a 3 in front of lead sulfate, okay, which would then kick up my my lead, and I have to go back and check that. So we can go that route. What if, let me change the color here. We'll keep it a blue. I got 3 sulfates on the reactant side. Well, what if I put a 3 in front of there? That gives me 3 sulfates, does it not? But that kicks up my lead to 3. All right, let's put my lead, let's do this. What if I put a 3 in front of to pick up my lead? That gives me 6 nitrate, okay? All right, so I go back to my nitrates, and if I put a 2 in front of nickel nitrate, guess what? I got 6 nitrates, and it gives me 2 nickels. Well, just by default, I'm good to go with the nickels because nickel sulfate requires 2 nickels, so that balances out. Okay, let me rehash for a second. Balancing double displacement reactions, follow the polyatomic ion, whichever one you want to follow. Okay, I followed the sulfates. I had 3 sulfates as reactant. I put a 3 on the right side to balance my sulfates, which in effect picked up my count for the lead. No problem. I came back to the reactant side, and I put a 3 in front of the lead to balance the lead. When that happened, what happened is now I kicked up my nitrates. Now I got 6 of them, okay? Because I got 2 in parentheses and I got a big 3 coefficient. That's 6 nitrates. All right, no problem. If I go to nickel nitrate and I put a 2 in front of nickel nitrate, that picks up my nitrates because I got a 3 nitrates in parentheses and I got a 2 in front of the whole molecule. That gives me 6 nitrates, which then kicks up my nickel. So I got to go back to the reactant side, and just by default, my nickel is balanced, okay? Because that formula is a nickel to a nickel 3 sulfate, and it balances out, okay? So double displacement reactions, those are the ones that are governed or determined by the solubility table. Balance them, follow the polyatomic ions. Now, I got this big old mess here. Let's see if we can clear it up a little bit and bring in the letters here. But hopefully by doing what I just did, you can see. So how I did it. First step, you got the words, you write the formulas down in ionic form, put them together properly in the right ratio, and obviously put the physical state. After that, follow the polyatomic ions to balance. Let's clear this up. All right, so that's what we got right there. Okay, so that's the reaction. This is an example of a double displacement reaction. Now, for your reference with double displacement reactions, if both reactants, okay, that you put together here, if both reactants are soluble, then there's no, let me restate that. If both products were soluble, based on the solubility rule, then we'll get no reaction. But here, one of the products was insoluble, and therefore we have a positive reaction. And it's pretty cool the way it works in real life. If you had a test tube with both of these reactants, nickel sulfate and lead nitrate, both clear solutions, I get them, I put them together, I get a powder that precipitates very quickly. Okay. And that is because the lead sulfate shows insolubility in water. All right, so the 6 types of reactions, and here they're given to you in generic form. Okay, so you can hopefully recognize them when you get an actual chemical reaction. Okay, so here, what we call a combination reaction. Normally, 99% of the time, you have 2 elements, A and B, that react to combine to give us a compound AB. Okay. Classic example of this would be, let me write one down, would be hydrogen. I'm not going to balance them. I'm just going to do a general reaction. Plus oxygen gives us good old-fashioned H2O. All right. If I want to balance it, I could put 2 right there, and we got we're balanced. Or are we? No. Now we're balanced. 2 elements come together to form a compound AB, in this case, water. Okay, classic example. Decomposition reaction. Okay, we have a compound that is broken down to the elements. And a classic example of that is water again. If you take water and you hit it with some electricity, put a charge through it, you would break that water down to produce hydrogen and oxygen. Okay? Hydrogen and oxygen. And that's why it's so important to find water out in space, because we can break it down and we can create oxygen because we need that to breathe, and we can use the hydrogen as fuel. All right? All right. And also too, hydrogen and oxygen together is a fuel. It's some of the fuels used in rockets. Combustion reaction. Okay, here's the thing about combustion reaction is for Chem 130. Okay, the only combustion we're going to be dealing with is combustion of what are called hydro. Let me change the color. That color doesn't stick out very well. I get lost in the background. Hydrocarbons. That's what these are. 1, these are compounds that are made up of nothing but carbon and hydrogen. Okay. X, the minimum X is 1. The minimum X and Y are whole numbers. The minimum value for X is 1 carbon, and the minimum value for Y is 4 for hydrogen. So what we have is the smallest hydrocarbon we have is methane, 1 carbon. But you're familiar with these because if you did a cookout with gas, you probably use propane that has 3 carbons. That's a hydrocarbon. Or if you have a lighter and you're flicking your Bic, you're using butane. That's 4 carbons. Okay. There's but it is combusting that hydrocarbon. That's what combustion reactions we're going to be dealing with. One requirement that any combustion reaction it needs is obviously oxygen, right? You can't burn anything without oxygen. So you should know that when you do a combustion reaction, oxygen is a reactant. Now for Chem 130, and I repeat, for Chem 130 only, the only products that you will get in the combustion of a hydrocarbon is carbon dioxide and water. And that's it. That's it. Okay. Yes, I understand your vehicle uses hydrocarbons. And yes, I understand that your vehicle produces carbon monoxide. But that's because our engine in our system is very inefficient. It doesn't burn oxygen efficiently. It doesn't burn hydrocarbons efficiently. I think our vehicles are probably in the range of 40 to 50% efficient, somewhere in that range. We can get 100% efficiency, but our vehicles have to run at a very much higher temperature, which is not good. Eventually, the engine will break down and metal will break down. So, and so only two products. One, for combustion reaction. One, hydrocarbons only as a reactant. Oxygen is a reactant because you need it to burn. And the only two products you get is carbon dioxide and water. Okay. Now I'm going to give you this information now. When we do an example, we will give you a more specific example. For the combination reaction and decomposition reactions, when we are balancing them, yeah, those two probably require more or less a trial and error number. Throw a 2 here, a 1 here, 3 here, and get your atoms to balance out. Unfortunately, the reactions for those will be not very complicated, so it'll be a trial and error. Eva, you have a question? You got your hand up. Go ahead. Hello? Did you have a question, Eva? Your hand was raised. No? Okay, I will lower the hand. Okay. And so we have trial and error basically for combination, decomposition reaction. If you guys have a question, don't hesitate, unmute yourself, and we'll get an answer. So trial and error for the first two. For the combustion reactions, we have a specific way to balance them. Okay. And we'll give you a number how to do it specifically, but it begins with first step, we balance the carbons first. Okay. Two, after the carbons, we balance the hydrogen second. And then third, we finally balance the whole thing by balancing the oxygens. Okay. So there is a systematic approach to balancing combustion reactions of hydrocarbons. Carbon, hydrogen, and oxygen is how you balance it. The other ones, we play with the numbers, the other two examples. But like I was stating, fortunately, they're not going to be that complicated that you're going to have a tough time, trying to balance them. All right, combustion reaction. Next example is an acid-base reaction. Okay, we talked about this in the chapter of acids and bases. And so what you have is, to refresh your memory, is an acid, which is normally coming from a covalent compound, okay? Reacting with a base, which is normally based on the Arrhenius base, is coming from an ionic compound, which contains the polyatomic ion hydroxide. And so the acid produces the proton, okay? And the net reaction is the proton plus the hydroxide gives us water. okay? And the corresponding salt, Ma, whatever it may be. So you always have an acid, you have a base, you always get water and the salt. To balance these guys, follow the acid, the proton, and the hydroxide. Okay. So sometimes the acid may have two protons, which means I need two hydroxides. Notice here what I write here. The net reaction is one proton per one hydroxide. So if I need 4, for example, protons, if I have 4, then I'm going to need 4 hydroxides, which is going to give me, guess what? 4 waters, okay? And so with acid-base reactions or neutralization reactions, follow the protons and the hydroxides. We'll have some examples of that here and how to balance it. Okay, the next, so that's 4 reactions, different types of reactions. The next one is what is called the single replacement reaction. Now, notice the trade here in generic terms. We have a metal here, M, as an element. So it's sitting there all by itself. And then we have another metal, and I'm going to give this a different color. Let's give it that color. Okay, but this metal is in ionic form. Okay, and look what's happened. The M in elemental form replaces the A in ionic form to give us a whole new ionic compound, MX. And then we regenerate A as an element. Classic example of this type of reaction is plating reaction. When you have, you may have jewelry that's plated with silver or gold or copper or anything, or chrome plating, any of that. That is an example of a single replacement reaction. What governs that reaction is the activity series. And if we go to the periodic table, on the bottom right side, above the solubility rules, you will find what are called the activity series. And it's a listing of metals. You'll notice here that it begins a list. There's 2 layers here, 2 levels. They're all crunched up, but you could stretch them out. And on the far left will be lithium, right there. I just highlighted that. That is the most reactive metal there is. And that is, lithium is more reactive than potassium, which is more reactive than barium, and goes on until you go all the way to the end where you find gold. Gold is the least reactive metal. Now, this activity series is relative to hydrogen, H2. And hydrogen could be in the form of either H2, the element, or water. Okay. So, and the way this works is this. Is, first of all, the ones in bold and underlined, those metals are extremely reactive. You simply have to place them in water and boom, they react. So normally we have to keep them under an oil material to keep them from reacting. They're so reactive. The other metals, starting with magnesium forward, do not require such harsh conditions. So magnesium to lead, those, to get those to react, we have to actually add a little acid to them, a little acid to get those to react. And above the hydrogen, which comes into play, carbon, copper, all the way to gold, those metals are very extremely unreactive. They take vigorous conditions to get those metals to react. Gold, as stated before, is noted as the noble metal. It is so unreactive, it really takes harsh conditions to get that gold to react. Very harsh conditions. And that's why gold that's been buried for thousands of years, when you take it out, it's still as shiny as the day it got buried. So unreactive. Okay. And we're going to get some examples of how this works. And as far as if this reaction will proceed as written. And that's going to be governed by the activity series. So already the reactions we've been talking about, to take the solubility rules play a factor, the activity series play a factor as far as reaction would a reaction proceed or not. So for single replacement reactions, as noted here, we look at this activity series. Okay. And finally, in that last example we did with the lead and the nickel example, we had a double displacement reaction. Notice here in written in general form. Now the subscript 1 and 2, that does not denote how many of M there is. It's just telling you we have two different metals. Okay. And so you can see that M1X exchanges partners with M2Y to give you now the new compound, which is M2Y. Okay. And so the M1 reacts with combines with the Y to give you M1 MY. I'm going to put these in different colors here so we can distinguish them. And then we have the X and the M2 combined to give us the M2X combination, just like we did that example. Okay. Now, if a reaction happens, one of these products, we don't care about what's happening with respect to the reactants. What we care about is the products. If one of them is insoluble, let's assume that's insoluble, and M2X is insoluble, which is governed by the solubility rules, then we have a reaction. If both the new products are both soluble, no reaction. Okay. Oh, okay. So those are the 6 reactions: combination, decomposition, combustion, acid-base reaction, single replacement reaction, double replacement. As far, I didn't mention the single replacement reaction. Normally, the single replacement, a little bit of trial and error. The reactions are very simple. You can do simple numbers. Double displacement, like we just explained, I did in that example, follow the polyatomic ions, because X and Y most of the time would be polyatomic ions. All right. Here's an example of a combination reaction. I gave one hydrogen and oxygen, but here's a different one. Phosphorus, we got oxygen, combined to form diphosphorus diphosphide. Okay. So we're going to balance this. That's a good example. Notice we got 2 elements to give us a whole new compound made up of those 2 different elements. Okay. A decomposition reaction. Here we have iron 3 oxide reacts to give us iron and oxygen. Okay. Iron 3 oxide, AKA rust. Okay. Rust. You can treat it, heat it up a little bit, and you break it down, and you will create iron, and you will create oxygen. Okay. So decomposition reaction, we have a compound, break it down to form their respective elements. And of course, balance them out. Combustion reaction. Okay. Here we have the formula for propane gas. Now, we don't need to know the actual structure. We know, we can just simply tell you that propane contains 3 carbons and 8 oxygens. Now, being a hydrocarbon, remember, combustion reactions, we deal only with hydrocarbons and oxygen. And so, here it is. All right, so we have C3H8. That is propane, okay, which is a gas, plus oxygen, because we are burning this thing up. It's undergoing combustion. All right, reacts to give us, remember, the only 2 products we get for a combustion reaction of hydrocarbons is carbon dioxide and water. Okay. All right, so that's the reaction. Now, remember, we have a set system to balance this. Number 1, balance the carbons first. So we have 3 carbons as a reactant. We need 3 as a product. So we put a 3 in front of carbon dioxide. That balances our carbon. Number 2, balance the hydrogens next. Okay. We have 8 hydrogens on the reactant side, but we only have 2 on the product side. Well, we can put a 4 in front of water. That gives us 8 hydrogens. So that balances up the hydrogens. So our carbons are balanced, our hydrogens are balanced. What is left is the oxygen. Well, obviously we only have 2 right here. And we have 6 coming from carbon dioxide plus 4 from water. So we have a total of 10 oxygens on the product side. But to balance the oxygens on the reactant side, very simple. We put a 5 in front of O2. Why do we put a 5? Because oxygen, remember, is diatomic. Now, if you might be tempted to put a 10, well, if you put a 10, now you got 20, right? So that would not work. So you just take half of what you need to balance the oxygens. So what does that tell us? That tells us that we have, are we balanced? Let's double check. We have 3 carbons, 8 hydrogens, 10 oxygens, and certainly 10 on the product side. 6 that are in the form of carbon dioxide and 4 that are in the form of water. Okay, so we are balanced. So the ratio here is 1 to 5 for burning of propane. Now, keep in mind, we are burning hydrocarbons, and this is just a crude example of a small example of propane, but vehicles burn much more higher chain carbons, hydrocarbons, which require a lot more oxygen. Because right here, we have 3 carbon chain requires 5 molecules of oxygen. And as we increase the carbon chain to combustion, we need more oxygen. So our oxygen level is dropping, right? Well, at the same time, we are creating more carbon dioxide here in this simple propane. For every molecule of propane that you burn, you are creating 3 molecules of carbon dioxide and 4 molecules of water. Okay. Well, carbon dioxide is a gas, and it's got to go someplace, and the only place it's going to go is going to the atmosphere. It can't go out in space because gravity holds everything in, all the gases in. Our plants that we used to have quite a bit of are dying away. We don't have as much. So because the plants would love this carbon dioxide, but it's not being utilized as much. And therefore our concentration of CO2 is going up. The only place it can go is up in the atmosphere. It acts as a blanket. We're also increasing our water vapor that's going into the air, plus all the multiple other gases up there, and it forms a blanket. Normally, heat from the sun onto the earth will be reflected and go out to space. But with that blanket up there of gases, it reflects back onto earth, causing temperature increase. Very analogous to your vehicle in the dead of summer when you drive up to school or work and your car's nice and air conditioned and you shut it off, you come back 8 hours later, 120 degrees outside, and it's pretty warm inside, right? Wow, that's exactly what's going on. Cars reflecting the heat, retaining it. So our temperatures going up, causing all kinds of problems. Anyway, here you go. That is the combustion reaction of a hydrocarbon. And to balance it out, we have a set system. Okay. And that is carbons first, hydrogens next, and then followed by oxygens. And that's what they're doing here. Now, always remember, when we're doing a combustion reaction, we are talking about hydrocarbons, CXH1, okay, which requires oxygen to burn, which the only 2 products you get is carbon dioxide and water. And oxygen obviously is always a reactant. All right. So you might just be given the hydrocarbons. Okay. So now you know what what are the products of a high combustion reaction, and what are the reactants of a combustion reaction. All right. Acid-base neutralization reaction. This is what we talked about, acids and bases in that chapter. Here now we're talking about them as a reaction. Okay, so we have an acid, like I stated earlier, normally an organic covalent compound reacting with a base. Okay, so the proton and the hydroxide react to give us water. Okay, so we have a reaction here. Asking you to complete the reaction. And like I stated earlier here, when we balance these things, follow the protons and the hydroxides. First of all, recognize that you're dealing with an acid, HCl. Normally, the proton is written first. Now, there's a few exceptions that the proton is not written first, and that's water, H2O. It's written like that by convention, H2O. It doesn't mean that H2O is an acid, okay? That's the only exception. But for us, 9 times out of 10, hydrogen written first would tell you and suggest strongly that you're dealing with an acid. Next thing is you got barium hydroxide. That's why you recognize you got a parenthesis here. A parenthesis should tell you by now that you have a polyatomic ion. So you look inside, you got OH. Go to the table, polyatomic ions. The OH is the hydroxide. This is barium hydroxide. Okay. And so note that there's 2 hydroxides. And like I said earlier, to balance these things, follow the acid and the base. Normally, as I stated, 1 proton plus 1 hydroxide, it's a 1-to-1 relationship, gives me 1 water. Okay? 1, 1, 1. All right, I got 2 hydroxides. That means that I need 2 protons. So I can easily put a 2 in front of HCl. Okay? Because if I got 2 of these, I need 2 protons to balance out, to neutralize the hydroxide and the proton. Which guess what? It gives me 2 waters. And so I got 2 waters sitting here. Okay? So I'm halfway there. Now I just simply have to write the ions of the salt. The salt here is going to be barium and the chloride. Okay, I know that barium is a +2 species, so I'm going to have a +2 charge. Okay. And I know the chlorides are a -1. Okay, it's a group 7. The group element 7 is going to have a -1 because it's going to pick up a proton. Okay, so putting barium chloride together requires me to have 2 chlorides for every barium. So that means that the formula for barium chloride is as follows. Okay. Now the question is asked, well, what's the physical state of barium chloride? That is where the solubility rule comes in. If you look at the solubility rule, you'll find that barium chloride is soluble. All the chlorides are soluble with the exception of the ones with the heavy metals, silver, mercury, and lead. But this is barium. It's not one of the heavy metals. So it is soluble. And water is being produced, so it's a liquid. We know that water is a liquid at 25 degrees, right? 0 degrees, water is ice, is solid. 100 degrees, water is a gas, so it would be a G. But we're at 25 degrees room temperature. All right, so now we go back and let's see if we can balance this. Let me clean up the mess a little bit here. Okay, we'll get rid of this, get rid of that. All right, you can see that. Okay, so we put a 2 in front of HCl, which gives us 2 chlorides. We got 1 barium, and we got 2 hydroxides, 2 protons, gives us 2 waters. The waters are balanced. and the barium chloride is balanced. So guess what? We have a balanced chemical equation. All right, let me clear up my mess. We got two protons as I showed, because we have two hydroxides, which gives us two waters, and we have barium chloride aqueous. And so we are balanced. And what do we do here to balance the reaction? We follow the proton and the hydroxide. Okay. I'll continue with what we got going here. All right, this is one of the weak acids we spoke about. Okay, phosphoric acid. And again, we got calcium, but this time parentheses, we got calcium hydroxide. So again, we have a base. Okay, so acid base. Now, before I know I'm going to get product here, H2O, because we got an acid base reaction. So I can write down water. Okay, and I know it's going to be a liquid because, again, acid base reaction. Now, what do I know? I got two hydroxides here, but I got three protons coming up. Okay, so like we did earlier with charges that are dissimilar, a plus and a two, find a common number. And so what if I put 3 in front of calcium hydroxide and 2 in front of phosphoric acid? What does that do? Well, that gives me 6 protons, right? And 6 hydroxides. Now I can put those together, and guess what? How many waters am I going to get? Obviously, 6 waters, just like up here. I got 2 protons, 2 hydroxides, I'm going to get 2 waters. Here I got 6 hydroxides, 6 protons, I'm going to get 6 waters. Okay. So now what I'm going to do is write the ions, because I don't want to put them together just yet. I got calcium. Okay. I know that calcium is a +2 because it's a group 2 element. It's a +2 as an ion. Also, I know that there are 2 hydroxides here, and each one is a -1. So obviously that confirms that calcium is a +2. The phosphate, since I lost my three protons, now I have PO4, guess what? -3. That look familiar for the polyatomic ions, phosphate. Phosphate, when it reacted phosphoric acid, H3PO4, when it reacts with a base, creates phosphate. Okay, now I have 2 dissimilar charges again. I got a +2 and a -3. Well, a common number. I need 2 calcium and 3 phosphates. So I can write calcium 3. I need a parenthesis because I need 2 phosphates. And there you go. All right. Calcium phosphate. Now, any idea if calcium phosphate is soluble or insoluble? You might need your solubility table. You will see that it is I won't say it. I'll let you look it up. Okay. Calcium phosphate. What do we got here? Okay, we got an answer. Insoluble. You are correct, Christina. Phosphates are insoluble. It's an insoluble column unless the phosphates are bonded with the big 4, right? Lithium, sodium, potassium, and ammonium. Well, it's not. It's combined with calcium. So we have insoluble. We write S. Okay. If you have a lot of phosphates in your water, this is part of the material that can cause ring around the tub along with our calcium carbonates. Okay. All right. So now it looks like we're balanced. We got 6 hydrogens. Let's check. Okay. I got a total of 6 hydrogens coming here. and a total of how many hydrogens do I have? 6 over here, do I not? 6 hydrogens in calcium hydroxide. So I got a total of 12 hydrogens on the reactant side. On the product side, 6 times 2, because I got 12 hydrogens in the form of water. Okay, so those are good. And I got 2 phosphates. Okay, on the reactant side, sure enough, I got 2 phosphates in the form of calcium phosphate. I got 3 calciums as reactants, 3 calcium as product. It certainly looks like it's balanced. Let's clear it up. We can see a little bit better than. Okay, there. That's what we went through to balance the bases in the proton. That gives us 6 waters, and we got a balanced chemical reaction. Okay, so this acid-base reaction, we follow the neutralization. All right, let's take a quick short break. Let's say 10 minutes. I got 212 right now on my computer. Let's call it 220. Okay. So let me stop, pause the recording. Okay, guys, I'm back. All right, let me kick it up a little notch or two. Knock this out because the next few chapters are extremely short. we'll finish those too. Anyway, so acid-base neutralization reaction. Here's an example of what type of reaction. Recognize you have an acid. Recognize you have a base. To balance them, follow the protons and the hydroxide. Okay. All right. Single replacement reaction, as I stated earlier in the general equation, is that you can see M represents a metal, is replacing another metal, A, which is in ionic form. It is an ionic compound, is bonded with X, whatever X may be. Now, if the way this works, again, like I stated, is the activity series, and you go through a series of questions you ask yourself when you look at this to determine whether a reaction proceeds. Okay, so the thing to remember is the most reactive metal for a reaction to proceed has to be. Let me do it this way. I want to make sure I get it straight. There's no confusion. If we look at this reaction and we compare the metal M and A, and we go and look at the activity series and determine which is more reactive. When we do that, step number 1, we determine which metal is more reactive, regardless of whether it's ionic or elemental form. And we determine that M is more reactive than A. Okay. Second question you ask yourself, is the most reactive metal in ionic form? Most reactive metal in ionic form, or is it a compound? That's the question. So we look here, we go back to the equation and we see that M is not in ionic form. It is an elemental form, okay? And so if the answer is a yes, the most reactive metal is in ionic form, then we get NR, which means a no reaction. If the answer is no, then we get reaction. Okay, let me restate that. Step 1, find the metal that is more reactive using the activity series. Okay, in this general example, we determined that M is more reactive than A. Step 2, ask the question, is the most reactive metal in ionic form? Okay, if the answer is yes, then there's no reaction because it is in the most stable form it needs to be in. Okay, if the answer is no, then reaction proceeds. And then that means that it's not in the most stable form and needs to be in ionic form to be more stable because it is the most reactive metal. In this example on top, M is not in ionic form, so we have a reaction that proceeds. Okay? When you put the reaction together, in this example here, we'll get specifics here in a minute. First thing to do, we know automatically that A is going to be displaced, so we can write A in elemental form, okay? But we don't know M, the formula for MX. So what do? Like we've been doing in the past, we write the ionic form first, and this be plus whatever X, plus 2, plus 3. And then A, whatever charge that would be, and then we put it together, okay, to give us MX, to make sure we put it together in the correct ratio, okay? All right. So let's work on it. So as I stated, there's the activity series of the metals that we're going to be dealing with, okay? We got hydrogen sitting here. We'll get some examples that use hydrogen to determine whether something is. Well, you do an example of hydrogen in down the road here. All right, let's figure out. Let's do an example. Okay. All right, so here's some more examples. Don't forget the states of the products and so forth. So we have nothing different than we've been doing. All right, and it's general information that I just stated. Probably the best thing is to actually do an example, and then we are, of course, we're going to balance the equation. Let's take this reactant here. Okay, we have zinc nitrate in the presence of sodium metal. Question is, will this reaction proceed? So step number one, look at the metals. It doesn't make a difference if they're ionic form or elemental form. We are comparing zinc with sodium. So here's sodium, and zinc is sitting right there. Okay? Using the activity series. Based on that, this says that step number one, sodium is more reactive than zinc. Okay? So for sodium, is it ionic? Is it in ionic form? The answer is no. Okay? It is in elemental form. So that means that reaction occurs. Okay? So what does that tell you as far as products are going to be concerned? One, zinc is going to come and become the elemental zinc. Okay? Because we are exchanging the sodium and the zinc. These two are being exchanged. Okay? Right now, zinc is in the +2 state. It's in ionic form. Now it's going to become in the 0 form, in oxidation state, because you become an element. Now, sodium, we know that sodium, okay, we're gonna put them together. Let me clear this up a little bit. So we understand there's going to be a reaction. Let's clear the screen here a little bit. Okay, and so we know the product. So I'm just going to put the products here. Zinc is going to be converted to elemental form. Right, and we're going to have sodium and the nitrate. Okay, because we're exchanging here. So before I put them together, I'm going to write them first in ionic form. Sodium is in group 1. We know that it will have a +1 charge. And the nitrates, we all know that right now that it's a -1 charge. So together it's a 1-to-1. So our formula will be sodium nitrate. Okay, and I know that sodium nitrate is going to be aqueous. Why do I know that? Because sodium, one of the 4, remember in solubility rules, anything bonded with sodium would make it soluble. Okay. And so now that's my formula. That's my new products. Okay. all I got to do now is balance. And in this scenario, follow the polyatomic ions. I got two of them, two nitrates. Guess what? Stick a 2 right there. All right. That kicks up my sodium with what? Put a 2 right there in front of sodium. I'm balanced my sodiums. My zinc's okay. They're balanced at 1 of each. I got 2 nitrates on both sides and 2 sodiums on both sides. I got a balanced chemical equation. All right. And let's do it there. Okay, I know the sodium is soluble and zinc is a solid. Okay. And as I stated, I followed the nitrates here, the polyatomic ions, put a 2 in front of sodium nitrate, that balances the nitrates, that kicks up my sodium. I had a sodium 2 in front of sodium metal, and now I'm balanced. Okay. So reaction proceeded. Now, what does this also tell you? If reaction proceeded in that direction, then the opposite direction will not work. What does that mean? Let's show you this way. What if I started off, instead of zinc nitrate, I started off with sodium nitrate and I dealt with zinc? Would reaction proceed? And the answer would be NR. Okay? How do I know that? Same question. Which metal is more reactive, sodium or zinc? Well, obviously, again, like we did, sodium is more reactive than zinc. Is the most reactive metal in ionic form? The answer is yes. It's already in ionic form, no reaction. Okay? Which is no reaction in this direction. All right. So being written in one direction with no reaction means that the other way writing it, you will get a reaction. Okay. Hopefully you can see that. Of course, it's not going to be 2 nitrates there because again, that implies sodium is a +2, which we know that sodium is not a +2, it's a +1. It's in group 1. It's a group 1 element. Only has 1 valence electron. All right. Okay, so let's take a strontium bromide and aluminum. So let's find the metals first and find out which is more reactive. So we got aluminum, which is right here, and strontium, which is right here. Okay. Question is, who's more reactive? Obviously, SR is more reactive than aluminum. Okay. Is the most reactive metal in ionic form? Answer is yes. It's strontium bromide. Okay. Therefore, no reaction. Okay. No reaction. But it does mean that the opposite direction will be a positive. Okay. That means, let's say I had aluminum bromide plus strontium. Question would be, would that reaction proceed? And the answer is yes, same thing. Strontium is more reactive. No, it's not in ionic form. So yes, the reaction proceeds. So we actually create aluminum plus strontium bromide. And we'll let you balance that out. Okay. All right. All right. So that's basically what I just stated. Now we have an example here of a metal with an acid, HCl. Okay. And so now what we are comparing is, in this case, aluminum and hydrogen. And so if we go to the table, we can see that hydrogen is right here and aluminum is right here. And so aluminum is a lot more reactive than hydrogen. Okay. And so aluminum is a lot more reactive than hydrogen. In this case, um, H2. So this means that this hydrogen is going to be replaced by that aluminum. And that means that the element, remember, we're doing a single replacement. And even though I said we're using hydrogen as our reference point, it's all these, the activity series is relative to hydrogen, okay? The elemental form of hydrogen will be H2. So one of the products I'm going to make is H2 gas. And the aluminum is going to replace the hydrogen. Okay, and so what we need to do is first write aluminum in ionic form. Right now it's elemental form. And then we know that, and that's a +3. Why? Because we know it's a group 3 element. It's going to have a +3 charge. And we know that the chlorides are -1. Okay, we know there's 3, we need 3. So our formula for aluminum chloride is, excuse me, is AlCl3, and it is soluble, so it's aqueous. And we know that H2 is a gas. All right. And so now all we got to do is balance it out. Okay, I got 3 chlorides sitting over here on the product side, got 3 on the reactant side, so I could put a 3 there. Okay, but that changes my hydrogen. So maybe I ought to do it a different way. Let me clear my okay. That is the products that I get. All right, so I can do this any number of ways, whatever way works best for you. But what is going? Don't forget your system here. Oh, sorry about that. I was going to say is this. All right, I had 3 chlorides up here. Okay, well, I could start off with put 3 here. That kicks up my hydrogens up to 3 hydrogens, but it kind of messes up my system here because I got 2 hydrogens on the right side. And I can't really balance it, this 3 and that 2. So if I do 6 here, okay, and I put a 3 here, that does take care of my hydrogens. 6 hydrogens, 6 hydrogens. All right. Well, that picks up my chlorides, which means now I put a 2 here that takes care of my chlorides. At 6 chlorides, 6 as HCl, which then I have to increase my aluminums. Okay. So that's basically how I had to do that. Let me rehash that. So initially, if I go, okay, what if I put a 3 here to balance my chlorides? Okay, sounds good. However, now I got a very dissimilar system here because I got 3 hydrogens and 2 here. All right, so if I double my, just like we had a dissimilar numbers in the past, if I put a 3 here, but I need to double this 3 to 6. Now I can balance my hydrogens. See how that one worked? This is what I mean by a little bit of a trial and error with respect to some of these balancing. Now, if, for example, you're done with the balancing and you come up with 4 here, 12 here, 4 here, and 6 here. Okay, that is balanced. That's true, that is balanced. But what you want to do by convention, you want the coefficients to always be used in the lowest terms, like in mathematics. Bring it down to the lowest common denominator. So the 4, the 12, the 4, and the 6 can all be reduced to 2, 6, 2, and 3. Okay. All right, so let us continue. Now, this summarizes, again, for the activity series, which is the most reactive metal. Once you determine which one of the most reactive metal is, then you ask the question, is it in salt form? If the answer is yes, then there's no reaction. If the answer is no, yes, you get a reaction and you exchange the metals. Okay. Write the new ionic compounds in ions first, so you can put them together in the proper ratio. Okay. Double replacement reaction. This is a classic example that we did earlier of the two. I showed you that was where one of the products is solid. You can see here that all that's happened is the A and the Y combine to form the AY, okay? And the B and the X combine to form the BX. Those are the new partners. Now, once you do that, then you use the solubility rules to determine whether AY or BX is soluble. In this example, BX is soluble, okay, but AY is insoluble. Therefore, yes, we get a reaction because one of the products is insoluble. If both products are aqueous or soluble, then we get no reaction, okay? We call this a precipitation reaction because the solid, obviously, we're dealing with an aqueous system. It's not soluble, so it will precipitate. You will actually get a solid in the bottom of your container, your test tube or your beaker, whatever you're running this reaction for. And that solid product is a precipitate, okay? Solid forms reaction will occur. No solid, no reaction, okay? So not necessarily, you have to learn the solubility rules, but learn how to use them. You don't have to memorize the solubility rules. So they're there in the periodic tables you have access to. So learn, refresh your memory. I've gone through them before, but I will rehash them one more time to make sure that we're in the same boat. We have two columns here. We have the left part column, which is the solubility. Okay. Number one, those four cations, whatever it is bonded with respect to anions, is making a difference what it is, always soluble. The same is true for the anions, the acetate anion and the nitrate ion. Regardless of what the cation is, it will always be soluble. Okay. So you got silver nitrate, copper nitrate, cobalt nitrate, acetate, all soluble. Now the halides, specifically the chloride, the bromide, and the iodide, 100% soluble, regardless of what the cation is. However, there are three exceptions to the rule, and that is silver, mercury, and lead. All those are heavy metals, the three heavy metals. Those guys, if they're bonded to any of those halides, it is insoluble. You get a precipitate. Okay. The sulfates, all the sulfates, regardless of the cations, are soluble, with the exception if the sulfate is bonded to calcium, strontium, barium, silver, lead. 1, 2, 3, 4, 5. Only 5 examples, sulfate examples, that are insoluble. All the others are soluble. Okay. Now, with respect to the insoluble section, that's on the far right here. Okay. Everybody here is insoluble. If carbonate, chromate, phosphate, they are insoluble regardless of the cation that is bonded to. The only exception is if they are bonded to any of the 4 in number 1 of the soluble column. Okay. And so carbonate, normally insoluble unless it's bonded to lithium, sodium, potassium, or ammonium. And the same is true for chromate and phosphate. Okay. Rest of the time, they're always insoluble. Same is true with the sulfide, unless the sulfide is bonded to the big 4, as I stated, or calcium, strontium, or barium. And so there are 7 examples of sulfide that are soluble and the rest of them are insoluble. Hydroxide, similar situation. Everything is insoluble except with the big four and calcium, barium, and strontium. And so there's 7 examples of hydroxides that are soluble, and the rest are insoluble. Now, with respect to these ionic compounds, when they're classified as soluble, 100% dissolved, strong electrolyte, okay? When they're classified as insoluble, weak electrolyte, because only maybe it varies, but maybe 95%, 5% soluble. And we'll have a few ions in solution, but the bulk of it is still intact and insoluble. Okay. So that's a rehash of the solubility rules. And that's what you need to work with respect to these compounds. Now, to determine these, the first thing you got to do is you got to put everything in ionic form, because without it, it's a little bit, if you don't put them together correctly, then you're not going to have the right formulas. Okay, so let's break them down. We got barium nitrate. We know that barium is a +2, okay? And we know that the nitrates, I'm going to put those down here. The nitrate, I'm going to put it down here because I'm going to combine them. The nitrates is a -1, okay? Let's do magnesium. I'm going to make that a different color. And then we got magnesium. Magnesium is a +2 also. It's in group 2 element. And then we got sulfates. We know that the sulfates are a -2. Go to the polyatomic ion. It will tell you that. I did that because those are the new partners that are come together. Because the barium will combine with the sulfate, and the magnesium will combine with the nitrate. So I put them together. So the new products would be barium sulfate, and that would be the new formula, right? Because I got a -2 and a +2. And then magnesium is a +2, so I need 2 nitrates here. So its formula would be magnesium parentheses NO3 2. Okay? So those are the 2 new products. Now, once I've done that, I now determine what is soluble and what is not. Well, let's do the bottom, nitrates. What do I know about the nitrates? Number 3, the solubility column, regardless of what nitrates are bonded to, they are soluble. So it's AQ. So we got no solid there. Sulfates. Normally sulfates are soluble. It's in the soluble column, but look at number 5. Unless the sulfates are bonded to calcium, strontium, lead, silver, and guess what? Barium. And so that means that barium sulfate is insoluble. And therefore, yes, we got a positive reaction because we have one product that is insoluble. Now what we're going to do is balance them out. And here, like I stated before, we did the earlier one with the nickel. Remember that one? Follow the polyatomic ions. I got 2 nitrates as reactants. I got 2 nitrates as a product. We're good there. Got 1 sulfate as a reactant, 1 sulfate as a product. We're good there now, too. Follow the, check the metals. 1 barium on both sides, they're good. 1 magnesium both sides, we're good. Just by default, this reaction is balanced simply because of the charges on the anions and the cations. And so we have a balanced chemical equation. Okay. All right. See how we did double displacement? We created the new products. Okay. Then we check the solubility of the new products. If anyone is insoluble, we have a positive reaction. If both are soluble, no reaction. Okay. All right. Let's take a look at this one. Another one here. Let's write down what the new products will be. And so we're going to exchange the lead and the iodide. And so here, which lead are we working with? Well, we know that Each nitrate's a -1, and there's two of them. So that implies that we are working with lead 2. Okay. And we know that the iodides are each a -1. So that means I need 2 leads for every lead 2. So the new product is lead hydride. Okay. All right. Then we got potassium and nitrate. Well, we know potassium is a +1, and we know the nitrates are -1. So the new products will be potassium and O3. All right. Once we've done that, look at the solubility. Potassium, number 1 here, it's always soluble, regardless of what the anion is. And then you got a double whammy here because the nitrates are also soluble. So potassium nitrate, always soluble. Now the iodide. Okay, look at number 4. We got iodide there. Normally it is soluble unless it is bonded to the big heavy metals, silver, mercury, and guess what? Lead. That means that lead to iodide is insoluble. And therefore, yes, we have a positive reaction. All right. Now, we got that set up. Let me clear this up a little bit here. Too much mess. Come on. Now what we do is we balance it. Well, in this example, I stated follow the polyatomic ions. Okay. We got 2 of them over here. It's a reactant. So guess what? What if I put a 2 in front of potassium nitrate? Okay, that'll work. That makes my nitrates balance, but that kicks up my iodide, potassium, excuse me. So I go back to the reactant side and I put a 2 in front of Ki to balance my potassium. So we're good with potassium, which kicks up my iodide. So I go back to reactants, and guess what? Because the nature of the beast, it's a lead 2. I got 2 iodides. I am balanced. Check my lead, my 1 lead. I got balance from the equation. Okay. Let me clear it up here and go reaction. All right. All right. Let's do a couple more. All right. New product will be barium and nitrate. Okay. Barium we know is a +2. Okay. And the nitrate would be a -1. And so that means I need 2 nitrates. So my new product would be barium, parentheses, NO3 nitrate. All right. My other one would be silver and the chloride. Well, silver always has a +1. And we know by now that chlorides always have a -1. So I can very simply put it together in the 1-to-1. And I got silver chloride. All right, let's check the solubility. What do I know about nitrates? Number 3, always soluble regardless of the cation. So this barium nitrate, always soluble. Okay. Let's take a look at iodide. Iodide, normally always soluble, except when it is bonded with silver, which tells us we got a reaction, silver chloride. Now we go through balancing. Give me 1 second. Okay. Again, here, follow the polyatomic ions. I got 2 nitrates as products. I need 2 as reactants. So my nitrates are balanced, which kicks up my silver. I go back to products. I put a 2 in front, the silver chloride that takes care of silver, but it kicks up my chlorides. Okay, and then I go back to products. Fortunately, I got 2 chlorides. Excuse me, my little partner is hollering at me. So it looks like I'm balanced, and it sure does. Okay. Let me clear it up, and we'll show the other one. Okay. So we got a balanced chemical equation here. Okay. All right. So that's the last example of a double displacement reaction. We're using solid relative rules. The key thing about this is when you write the new products, write them in ionic form first so you know how to put them together properly. Once you do the right formula, then go to the solubility rules, determine who's soluble, who's not. Okay? Give me 1 second. Okay, I'm back. Okay, as I was stating, create the new products, write them in ionic form, put them together in the right ratio. Once you do that, you got the right formulas written together. Check the solubility rules, find out who's soluble, who's not. Any one of the products is insoluble, you got a positive reaction. You find out that you have both of them, whatever new products you made are soluble, no reaction. Okay. All right. Which brings us to this term, what we call redox reaction. Okay. Redox reaction is a general term given to a lot of these reactions we talked about, because many single replacement reactions, many combination reactions, decomposition, combustion reactions also classified under the umbrella of a redox reaction. And the term comes from oxidation and reduction. It's a combination of the terms. Okay, shorthand for reduction and oxidation. Well, what does that mean? Okay, well, oxidation is, simply put, I'm going to use a general reaction. If a element, for example, or a species reacts, something happens to it, and it loses an electron. Okay, so one of the products is an electron. It becomes a positive charge, right? A lot of the metals lose electrons. They undergo what is called oxidation. So loss of electrons, one way I look at it is electrons exit the building, exit, get out of there. A lot of metals that undergo loss of electrons, that process is called oxidation. Okay. Now, there are some species, as we well know, a lot of nonmetals. What do? Okay. They gain an electron, right? And so they end up with a negative charge of sorts. We call that reduction. Okay. So loss of electrons, gain of electrons. Loss of electrons is oxidation. Gain of electrons is reduction. And hence those two terms, they break it down, take RD and DOX, and you get redox. Redox reactions occur simultaneously. There isn't an example where one by itself loses an electron. Wherever something loses an electron, something else will gain that electron. As we speak, if you're running off your batteries right now, there's a redox reaction occurring in your battery. And one side, some of the compounds in your battery are losing electrons, and then the other side, they are picking up the electrons. That's why you got a positive pole and the negative pole. Okay. So they occur simultaneously. They're the yin and the yang of chemistry. They cannot occur by themselves. They occur simultaneously. Okay. So when we talk about reduction, another way to look at it, when you lose an electron, your charge oxidation number drops. It goes low. You know, we can look at it in terms of a scale. You know, we have a scale. Here's 0, right? And we got -1 going down, -2 going up. We got +1, +2, right? So when something loses an electron, let's say you're at 0 and you and the oxidation, let me restate that. When you gain an electron, you undergo reduction. So your oxidation number gets reduced. Okay. Say, for example, you're at zero state right here. Okay. And you gain an electron, that's called reduction. Your new oxidation number becomes negative if you gain one. So your value drops, so to speak, in the scale from positive to negative. See how that works? Even if you're positive, you're a positive one and you gain an electron, and you gain, let's say, 2 electrons, and you're a +2 and you gain 2 electrons, your oxidation number drops to 0, right? The value goes down. Oxidation is the opposite. Oxidation is loss of electrons. So let's say you're at 0 and you lose an electron, your charge or your oxidation number goes to a +1. If you lose one, right, your number goes up. Your charge goes up. Even if you're -2 and you lose an electron, then you go to -1, right? Your value goes up. And if you lose another one, you go up to 0. You see? Anyway, the point here, you can't, each one occurs simultaneously. They occur together. You can't have one and not the other. Refresh your memory on the oxidation numbers. Okay. Using the periodic table, we know that all the elements up there have a natural oxidation number of 0. Have equal number of protons, equal number of electrons. Okay. We know that in group 1, all the metals have a +1. All the metals have a +2 for group 2, right? Because we went through this scenario. What kind of charge their metals? They're going to lose electrons. And group 3 metals will end up with a +3. That's the group 4 that it's on the fence. You know, they have 4 valence electrons. They have the option, depending on the reaction conditions, to lose those 4 electrons to give them a +4 charge, or to gain 4 electrons to give them a -4 charge overall. So they can vary from a +2 to a -4. After the group 4 area elements, everybody loses gains electrons. What am I saying? So group 5 always pick up 3. Group 6 always picks up 2, give you a -2. Group 7 always picks up 1. Okay, just like we spoke before, we went over this in the past. And then, of course, group 8, which is the electrons that the noble gases, they got the octet fulfilled. Nothing's going to happen. They're happy. They're not going to. It's going to be tough for them to lose electrons. And don't remember that helium has a duet. All right. Then I also gave you 16 elements that give you a constant charge. The ones from group 1 and group 2, that's 12. Then I also told you silver always has a +1, cadmium and zinc always have a +2, and then we added one more. Aluminum always has a +3. So those are the 16 elements. And now those are important to know because we don't need to use the Roman numerals to determine which oxidation number we are working with, because those guys always have that constant oxidation number. All right, so oxidation, again, losing electrons, the charge goes up. And that example here, we see that copper starts off with a 0 charge and it ends up with a +2, okay, because it lost 2 electrons. So solid copper is oxidized, okay. When that happens, solid copper is what we also call the reducing agent. It itself became oxidized because it gave up the electrons. So that means those electrons are going to be used by somebody else, something else, some other element. And they're going to pick up those electrons. Well, therefore, copper now is the reducing agent because it supplies the electrons that another species is going to gain, which is the reduction of that other species. Okay. Reduction, the charge goes down. We're gaining electrons, so the charge goes down with respect to value in the mathematical terms. That's why it's got a negative 2 charge. Okay, so sulfur, for example, picks up 2 electrons. Now it becomes sulfide with a negative 2 charge. So solid sulfur in this example is what is reduced. The fact that it is reduced now makes it the oxidizing agent, because the fact that it picked up the electrons causes something else to become oxidized. Okay. So let's have one chemical oxidized and one always reduced. We can't have one without the other. So what is specifically oxidized and what is specifically reduced is always the reactant. It had nothing to do with the product, just the reactant. Okay. So what if the question is asked, what is oxidized, what is reduced? It's always going to be one of the reactants. And it's going to be the whole compound of one of the reactants, not specifically just the metal. If it's in the copper chloride format and copper goes from a +2, for example, to a 0, then it is copper chloride that underwent reduction. Okay, not just the copper. And we have to figure out the charges. All right, well, let's take an example of this. We have copper 2 plus iron to give us copper solid and iron 2. Well, first of all, you might ask yourself, I'm always a skeptical kind of guy, and I say, how do I know this reaction proceeds? Well, if you go to the activity series, you'll find that iron is a lot more reactive than copper. And then here, iron is not in an ionic form, therefore reaction proceeds. Okay. All right. So what we have here is copper going from a +2 to a 0 state, oxidation state. Okay. So in order for that to occur, copper 2 must have gained 2 electrons, right? I got a +2 value. I want to make it a 0. I got to add 2 negatives to make it 0. And that is what's happening. It gained 2 electrons. The other one, iron, starts off with a 0 oxidation state. It is the element, but now becomes iron 2 because it gave up 2 electrons. Okay. And so what happens is iron 2, oh, stop 1 second, somebody else. Okay, I have to do something real quick. So to rehash, copper 2 undergoes goes from a copper 2 state to a 0 state. Iron goes from a 0 state to a +2 state. So therefore, iron is oxidized, copper 2 is reduced, which makes copper 2 the oxidizing agent, and iron solid is the reducing agent. Okay. Here's a real life example. These are a platinum compound that's actually used in analogs of these are used in cancer treatment. But in this example, we have CO, which is cobalt. We know NO3 is nitrate, obviously, right? And there's 3 of them, so therefore that must be cobalt 3 nitrate. So look what's happening to that cobalt. It's in the +3 state, okay, and it goes to a 0 state, okay? Remember, +3 state. How do I know that? Because, and I'm going to rehash that so you can remember this. We know that the nitrates each have a -1 charge, and there's 3 of them. So there's a total of -3 in the nitrates. That implies that cobalt has to be a +3. Okay. The platinum went from a 0 state to a +3 state. It has lost electrons, okay? Lost 3 specifically electrons and gave it to the cobalt. So what is oxidized is the platinum. Platinum is oxidized. What is reduced is the cobalt-3 nitrate. And therefore that makes it the oxidizing agent. And then we have the reducing agent as platinum. All right, so again, the name here, as I mentioned, is cobalt-3 nitrate. Okay, there are videos on the course website with respect to predicting products and looking at this particular chapter. So obviously I'm going to put this chapter up, but there's Dr. Kim who has her her method of teaching, her manner, this particular topic. By all means, feel free to get up there and listen to her version of this video. So the more versions you get, then maybe the better grasp you'll get of this particular topic. To summarize everything, get familiar with the solubility rules and how it works. The same with respect to the activity series, okay? Be able to recognize and balance combination reactions as when two reactants, specifically two elements, come together to form a compound, and recognize a decomposition reaction. Normally that is a compound that is broken down through the elements, okay? We talked and we did some examples of single replacement reactions, recognize the single replacement, be able to write the products and to obviously balance it. Okay, and the double replacement reaction. Now, the single replacement reaction, you need the activity series. The double replacement reaction, you need the solubility rules. Okay. We talked at length about acid-base reactions. That's the reaction between protons and hydroxides. Okay, to balance those, follow the protons and the hydroxides and the waters, and that would by default balance that reaction. We talked about combustion reactions. For us in Chem 130, when we talk about combustion, we're dealing with hydrocarbons, and those are compounds that have nothing more than carbon and hydrogen. Okay. And it's a combustion reaction. So obviously, you need oxygen to burn, and the only two products that we're going to make is carbon dioxide and water. Okay, and be able to identify in these reactions what is oxidized, what is reduced, and then respective agents. Okay. All right. With that in mind, congratulations, folks. You are done with chapter 10. And any questions at this point? And what we need. Now, this particular chapter that I'm going to talk about, any questions before I continue? Very short chapter. We'll get done with this here in no time. Okay. No questions about what we've done so far? Okay. Well, let's talk about an area of chemistry called thermodynamics. Now, point to make here is that we're going to talk about the tip of the iceberg in this particular field, because this field is humongous. So we're just touching on a little bit of it. Now let's look at the word itself, thermodynamics. If we break it down, we look at dynamics. The term itself, its meaning, we're talking about maybe some movement, how things interact with each other, the dynamics of something, right? Okay. And so thermal, that generally means heat. If it means heat, we're talking about energy. And so we're looking at reactions with respect to energy and how they interplay and how they interact. Now, we tend to think, that we can simply put A and B together and voila, magically we do some Harry Potter stuff and we make a compound. And I wish that was that easy. It turns out that reactions are pretty complicated, extremely complicated, because for them to occur, for a reaction to occur, especially as an organic chemist myself, trying to make something, trying to make a compound, we have so many factors that have to come into play. One of the big factors, orientation with reactants to each other. The best analogy I can think of is shooting pool. I don't know if you ever shot pool, call it billiards. You're trying to make a shot. You got the ball, you got the cue ball. You're trying to make a corner pocket or even a side pocket, and you got to hit it with the right angle and the right force. If you don't hit it with the right angle, you're going to miss that pocket. If you hit it too hard, you're going to make that ball not go in that pocket, take it out of there. Or if you don't hit it hard enough, it's not going to go in the pocket at all. So I I I look at chemistry as I'm shooting pool. Really, think about it, because I have to have the right orientation. I have to have the right amount of energy for reactants to come together to form a product. Okay, to form a product. So, for example, we have a theory called collision theory. Okay. And here we have an example of two looks like two diatomic molecules that are coming together to form a product. So we have this diatomic. Let me change the color a little bit. It's not coming out very well. Okay. We have this diatomic coming together with this diatomic. All right. Eventually, we want to create these new products. Okay. And you can see that we got to break a bond here in order to create a new bond. So we enter this intermediate, where this intermediate, you can see we got bond breaking and we got bond formation. That intermediate has a specific name. We call that the transition state. Okay, the transition state. It is a point in this reaction process where you are bond breaking and bond formation. Notice the orientation has to be just right. If this thing was skewed just a little bit, then we wouldn't get product. We wouldn't get what we're trying to make. A lot of chemical reactions that occur in your stomach to digest food are I'm surprised that they even function, because they have to come in together with the just right amount of orientation and energy to break down. Well, there's a lot of things what we call catalysts or enzymes in our stomach to help us with that. But think about it. Let's say in the room you're in right now, whatever room you're in. Let's say you got two molecules, maybe the size of a tennis ball. And so you're in your bedroom or you're in your house, and that represents your reaction vessel. Now, the idea is you got a blue tennis ball and a yellow tennis ball. They're supposed to come together to form a product. Well, think about it. If I put these two tennis balls and they're floating around in your house, for them to come together, floating around your house, that probability is pretty low that they're going to, if you got a big house, there's a probability they're going to come together to make a product. Yeah, there's a finite amount that, yeah, they'll eventually hit together, but it's pretty low. So how can we increase the probability of those two coming together? Well, maybe one thing we can do is add more tennis balls of the same color so they can come together. Okay. Another thing we could do is maybe heat up the room, get it hot. Because what happens? These molecules that are kind of just floating around, we heat them up, they're going to move faster. And if they move faster, you increase the probability of them coming together with the right amount of energy and the right amount of orientation to make a product. So there's a lot of variables involved to get things to work, to come together. And that's just two reactants. Some reactions require 3-4 things to come together, which makes it more difficult. Okay. So a successful collision in our theory results in the reactant bonds breaking and forming new bonds. Okay. So we have to increase the number of collisions. And that's one of the problems we encounter in the lab because we put two reactions together, they start at room temperature and then pick out samples and analyze it and find out if we're making anything. Sometimes leaving it alone at room temperature, it may take days for that reaction to proceed. Sometimes we heat it up a little bit. If we heat it up, we run into potential problems. Is that the product we make may decompose at a higher temperature. So yes, we make the product, but because it's a higher temperature, it breaks down. So we got to be careful with that. We can increase the successful more collisions, adding more material. Now we got to have enough energy for these to come together. That energy has a specific name. We call that activation energy. That's the minimum amount of energy necessary for two reactants to come together to form product. Okay. And again, as I stated, the molecules have to be orientated in a certain manner. Yeah. So we can increase the rate of reaction by adding more material. As I stated with that example of the tennis balls in your home. I want those two to come together. But if I only got two and you got a big home, the chances of them coming together is pretty low. Okay. Okay. The activation energy, and I'll give an example here, is the minimum amount of energy necessary for a reaction to proceed to give you product. Okay. And we're going to show that graphically here in a bit. All right. So what do? We can increase the temperature, make the molecules move faster, and gives the higher probability of them coming together. That's one factor we can do. No problem. And add more material. We can add a catalyst. A catalyst itself is not really directly involved in the reaction. What it does, it lowers that energy requirement, that energy of activation, to a lower level, so we requires a minimum amount of energy. Some catalysts are pretty destructive. Personal note here, in graduate school, I was doing what this is called kinetics. In other words, we put two reactants together and we pull samples out and we study and we analyze them and so forth. I had run this reaction numerous times, not a problem. And this one time I did another run because you could do multiple runs, and I put everything together. I put everything into a heated bath. I want to keep constant temperature, and they're all in tubes. And as soon as I put the material in the bath and I took one step back, that thing went boom, and it created quite a bang, and it created quite a mess. And fortunately, I just stepped out in the right time because, and also I was in the hood. What had happened was this reaction is very sensitive to metal, so I had to go through a procedure of cleaning my glassware to remove any residue metal. Evidently, I didn't do a good enough job, and I left some residue metal, which caused the reaction to go very fast, and that it was a catalyst. That reaction proceeded normally at a normal rate, but with that metal, it caused a reaction to occur quicker, and so quick it went boom. Okay. So catalyst and lower the energy of activation. So to define that energy of activation again, that is the minimum energy needed to react between reactants to products. Okay. Now, equilibrium reactions, we're kind of touching this a little bit when we were talking about material that was weak solutions. Okay, we had a double arrow, meaning that the reactants and the products go in both directions at the same rate. Okay, so there's an equilibrium that's happening. There's an equilibrium that's happening in your body with respect to maintaining the pH. Okay, there's a reaction that goes in both directions, so we want to maintain that pH in your blood system. Now, we have this transition state, and we have really 1, 2, 3, 4, 5 things to really put on the diagram here. All right, so first things first. Let me do this. If I were to follow a reaction, what I'm doing is I can measure the energy reaction, have a graph. And the graph, I can plot the data. That's terrible looking graph, but this is energy units, right now, arbitrary energy units. And then that's along the y-axis. And along the x-axis, we call that the reaction coordinate. In other words, if any given time, most of this is time really, any given time I take a snapshot, if I were able to take a snapshot of a reaction, I can take measure the amount of energy at that particular spot. And I collect that data over a given time period, and I end up with a graph that may look something like this. I start off my reactants at this stage, okay? I let the reaction proceed, and I got energy that goes up, and then after I'm done, I end up down here, and my products are down here. So my reactants, I'm going to name R. My products end up somewhere over here, okay? Now notice I can extrapolate, do a double dot, come over here, and if I put a scale, 10, arbitrary scale, 10, 20, 30, 40, 50, 60, 70, 80 energy units. We're not concerned about what specifically, but it's just energy units. You can see here that at the end, at the reaction, that my products, if I extrapolate that graph, I end up with 10 energy units is where my products are. I begin my reactants, extrapolate, maybe at about 20 energy units, okay, roughly, okay? I'm putting numbers in here so you can graphically see this. Now, up on top up here, this is my TS. This is my transition state, that picture we showed earlier. That is the state where I got product qualities and reactant qualities. It's the tip of the heel there. Okay, that's where I'm getting the bond breakage and the new bond formation. That's my transition state. Now, every reaction has a transition state, and even that reaction has an X amount of energy. And for our argument's sake, in my scale, which is not to scale, it's approximately 80 units of energy at the transition state. Well, if I look at where my reactant started and I extrapolate out a little bit, and then I go from my transition state to where my reactant started, I have transition state minus my reactants. Isn't that roughly 60 energy units, right? Because my transition state is at 80, my product reactant started at 20, so the difference there is 60. So that is called the energy of activation. That energy is the amount from where my reactants were to the transition state, okay? And I can calculate that because I know the energy of my transition state, which is 80, and the energy state of my reactants is 20, so that difference is 60 energy units. That is the minimum amount of energy necessary to become products, because now the rest is downhill. Now, if I go from where my reactant started and where my products ended, which is basically this distance here, we have this thing called delta H. That is the energy of the reaction, okay? Now, delta means the change, which is basically the energy of the products minus the energy of my reactants. Well, you can see here that my products end up at 10 E, and my reactants started off at 20 E. And guess what? 10 minus 20 gives me a negative 10 E. The important part about here, there's 10 units of energy difference between the reactants and products. But more importantly, it's negative. Okay? Negative. That tells me that this is an exothermic reaction because it gave off heat as a negative. Delta H is negative. It gave off heat. The thing to remember, you don't have to go through this numerical exercise. I just showed it to you to tell you how we come up with these values. But you can graphically see that the energy state of my products is much lower at the end than my reactants began with. And so I'm going to end up with the negative energy of delta H, energy of the reactor. Okay. My energy of activation is always going to be positive, always going to be positive. Okay. And so I have an area here. I've been able, I can label my reactants, I can label my products, be able to label where my transition state is, label my energy of activation, and be able to label my delta S. Okay, delta H, I should say. Okay. And that being an exothermic reaction means it gives off heat. If you go to the pharmacy and you buy a hot pack and you break it, you get a reaction that occurs, it gets warm. It's exothermic. This would be the energy profile of that type of reaction. Okay. Let me clear up my mess. Got a little messy there. Okay. So delta H is the change in heat energy. Basically, they call it the energy of the reaction. And that is the energy of my product's heat minus the energy of the reactant's heat. We call it heat, but keep in mind, energy and heat, we interchange the term, okay? Because, heat is energy, energy is heat. Okay, transition state is that halfway mark between bond formation and bond breakage, okay? When it's endothermic, excuse me, we talked about this. Heat is a reactant. Heat is required for the reaction. It's taken from the heat and it gets cold. I use that analogy of the cold pack. You go again to the pharmacy, buy a cold pack, you smack the container, the package, it gets cold. It's an endothermic reaction. It takes energy from the environment for it to react. Okay, exothermic is heat or energy is a product, and therefore it releases heat, and it gets warm. Okay. This here, as I went through the exercise, delta H, it will be negative because our product's energy level is lower than the reactant. So products minus reactant gives us a negative value. Hence, it's exothermic. Okay. In this example, if you look at this, you can see that the product's energy level is at a higher energy value than the reactants. And if I do products minus reactants, guess what? I get a positive delta H. Okay. And hence an endothermic reaction, positive delta H. And so it's endothermic. So this shows the diagrams for both exothermic and endothermic. Exothermic is listed on top, endothermic in the bottom. Okay. Here again, note the difference. The product energy of an exothermic, this is exo. Okay, it could be a negative delta H, being equal to negative. Okay, because the product is lower in energy level than the reactants. The other one, this would be endo reaction, endothermic, because the product energy level, which is about right here, is much lower, is higher. The final energy level is higher than where the reactants began. Okay, and so delta H here would be positive, and let me write delta H up on top would be negative. Okay. All right. So be able to identify these positions, label the reactants, the products, where delta S is, where energy of activation is, where delta H is, and then by looking at the graph, determine is it endothermic or exothermic, and whether delta H will be a positive or a negative value. Okay. Now, with respect to a catalyst, as I mentioned earlier, all a catalyst does is lowers that energy of activation. Recall the energy of activation would be right here. And so we have that versus what it normally is. Okay, you can see that the energy has been greatly reduced. So a lot of catalysts help reactions to occur. Your vehicle, for example, your catalytic converter, which be careful because people are stealing those and cutting them out. They have rare earth metals and they're quite expensive. Your catalytic converter is utilized to remove some of the gases that are being emitted from your vehicle. The enzymes in your stomach act as a catalyst. Now, they themselves do not do anything to the reaction specifically. All they do is lower the energy of activation, then they release and then go on and help out another reaction. Okay. All right. With that being said, congratulations. You are done with chapter 11. On to chapter 12 next week, and they'll probably knock out 12 and 13. So you are done with 11. We will do, well, we will start 12 next week. Okay. And don't forget your exam today. You have to tomorrow, 10 p.m., I believe. And let me stop this.